So here are the official goals. I'm going to introduce you to the idea of dynamic modeling. Why do we call it dynamic modeling? Why is it so important? And we're going to talk about the SIR model family that Steve has already introduced you to as a tool for that, and talk again about some of the things that we learned from it. We're also going to demonstrate, we're actually going to create a model here today live, and I just want to stress that I have absolutely no reason for me to be nervous about that. So dynamic modeling is the idea of connecting processes that happen at the individual level, and usually individual events, like this foolish child reaching out to touch this wet-nosed child. That's an event that happens at the individual level, to population level processes that happen at a bigger time scale and over a larger period. So this is a very nice time series of measles reports from England and Wales. Steve has shown you similar pictures. And there's some key ideas here. Patterns like this emerge from individual events like this one. And it's really hard to understand those links. And dynamical models are the tool we use to do that. We ask if we have rules for what's happening at this level, what's going to emerge at a higher level. And if you're doing that, it's a dynamic model. And what we're showing you are some examples of dynamic models, but really the broad idea of dynamic models is the thing, and there's many ways to do that. And we'll be talking about a few, but hopefully giving you indications about a few more. So our SIR model divides people into susceptible, meaning they can get the disease, infectious, meaning they have the disease, and we're assuming, we're not differentiating. We're assuming either that everybody who has the disease is infectious, or we're assuming that we can average over that fact without losing too much detail in our model, or people can be recovered. And we're going to assume that people get better independently. So I just have a black arrow from I to R. If I'm in I, I'm on my own. I'm eventually going to travel to R. But this little blue arrow indicates influence. We assume people don't get sick, don't get infected independently, but instead are infected by contact with an infectious person. And that's what this blue arrow indicates. And this is a simple model that incorporates like the fundamental thing that makes it an infectious disease. And importantly, so one of the themes of this lecture is don't be afraid of differential equations. And there's two ways in which people are afraid of differential equations. One is they think that differential equations are big and scary, which they're not. I'm going to explain to you that you're not allowed to be afraid of them in that way. But the other way is they think that differential equations are better. There's this history in this field particularly of thinking that the differential equation model is the real model, and if you're doing something else, you should apologize for it. And that's basically wrong too. There's a lot of ways to make a dynamical model, and which model you want to use depends on what question you want to answer. And here, I'm going to claim I'm thinking about this model before I've even implemented it dynamically. I'm going to claim that this already gives us tools, even before I say exactly what my dynamical rules are. Just the fact that I'm assuming people get better independently but get sick while contacting an infectious person already allows me to ask questions like, if I run this model until the end, until things stop happening, what's the final result? And so let me ask you that. What would happen if I started a model like this, let's say with some people in S, some people in I, and some people in R? What's going to happen when it's done, when I'm done this process? Is it acutely immunizing? Yes. I'm going to say that when people, I'm going to claim that I've sort of answered the question because people, when they're in I, they move to R at a certain rate, and I don't let them get out. If they were getting out of R, I would show you an arrow. And that's important. We try to use diagrams in this course in a structured way, and you are Catherine with a, is Catherine with a K also here? Darn it. And Kathleen is also here. So we're going to work on nomenclature. I was thinking we'd just call you C and you K and you Kath, but I'm going to let the three of you sort it out later.
So to answer your question.
Yes, please.
Well, I'm not sure if I can accurate. Well, okay. Given only your diagram,
yes,
you will end up with a bunch of recovery.
Okay. So that may be true, and it would certainly be true if we didn't have this blue arrow, right? If there wasn't for this blue arrow, there's nothing to do when you're in S but move to I. There's nothing to do when you're in I but move to R. But with the blue arrow, what we find is, with the blue arrow, what we find and what Steve said, and it's pretty general, is that if there's not enough people in if there's nobody in I, you stop moving out of S, right? And so in general, you could wind up with everybody in R, but more typically, you would end up with some people in S and some people in R. And we can ask, based on this model alone, when does the disease increase and decrease? And I feel like I'm getting stuck on this slide, so I'm just going to say the disease is going to increase in general when we have more coming into I than going out of I, which is going to be, in general, if we have a lot of susceptibles, the disease is going to increase, and if we have fewer susceptibles, the disease is going to decrease. And this is a perfectly valid model, and you can even go further than this. Without constructing equations that you can simulate through time, you can analyze just the conceptual model, and that's important. The model is not the ODE. The ODE is one way to instantiate the model. And now we're going to talk about that one way to instantiate the model. So to actually make a model that we can simulate and ask how things are changing through time, we're going to need to make specific assumptions about how recovery and transmission operate in time. And the ODE is not something to be afraid of. It's not the only way to do it. It's not always the best way to do it. Conceptually, it's the simplest way to do it. You don't need a time scale. There's a lot of details that you have to worry about in any other model. The ODE is the conceptually simplest way to do it, but you may do it another way, either because you feel the other way is more realistic, or because conceptual simplicity is not the only thing you're worried about. On the spreadsheet, I'm going to make a discrete time model, which in some ways is conceptually more complicated, but in terms of actually putting it into a spreadsheet is a lot easier. And that can be fine, right? Our goal is to construct the model that's useful and good enough for the current application. There was a long, and I felt slightly disconnected quote from Einstein, which is frequently misquoted. But I like the misquote far better than the quote. The misquote is, your model should be as simple as possible, but not simpler. So, to instantiate the model, we're going to assume that infectious people recover at a constant per capita rate, just like Steve did. So it means it doesn't matter how long you've been sick, your instantaneous probability of getting better the next second is always a constant. And that rate is going to be, by per capita, I guess everybody knows what I mean, but I mean per person, right? So each person has an individual rate of gamma. So if we have I people in box I, then the total rate, the rate we're going to put into our population equation, is gamma times I. That's the rate in which people are moving out of box I. And the mean time that you're going to stay in the box is D. And these quantities have units. Gamma is a pure rate. It has units of 1 over time. D is the duration of infectiousness. It has units of time. Susceptible people, we're going to assume, get infected by going around and contacting people. So our conceptual model is that the susceptibles and the infecteds are all walking around, they're going to work, they're taking buses, they're shaking hands, and there's a certain rate at which they make contacts which are relevant to this particular disease. And what a contact is going to depend on what your disease is. For example, I just coughed, and now I'll shake hands with some of you. Of the people I contact, if I'm a susceptible, some of them are infectious, and of the infectious people I contact, some proportion of these contacts are going to be effective. So I'm going to define an effective contact exactly as a contact which will transmit the disease, assuming one of the people involved is susceptible and one of the people involved is infectious. And so the per capita rate at which susceptibles become infected is CP, it's the contact rate times this proportion of people that you meet who are infectious times this probability, and at the population level, that comes out to beta SI over N. Are you Jeanette?
Yes.
Okay, good. I was hoping you would, I can't see you in the light, but I was hoping you're here because a lot of this relates to the questions you asked at the lecture. Sorry, I have detracked myself. So this is the rate at which individuals are leaving, and this is, since it's, again, a per capita rate, we're going to multiply it by the number of people in the box to get our equation. I'm just going to say it's been conceptually useful to me to think about transmission from the other point of view. So we just talked about susceptibles walking around, meeting people, shaking hands, what's the probability? I'm now going to think about what if I wanted to focus on the infectious individuals? So they're walking around, right? I just coughed in my hand, and I'm going to try to shake somebody's hand. We're supposed to cough in our elbows now, which is such a good idea. And it's only like in the last 20 years that somebody thought of that, right? Like I was taught as a kid to cough in my hand. Why? Why is that the right thing to teach a kid? Sorry. So infectious people go around contacting others at rate C. We're going to assume for now these rates are the same. Things get complicated if they're not. Some of these people are susceptible, and some proportion of these contacts are effective. It's exactly the same. And the interesting part is we get a per capita rate of infectious people infecting people, which is relevant to Steve's thing, are effective. But we can also scale that up to the population. And if our simple model is consistent, and it's always good to test yourself, if our simple model is consistent, that should give us the same answer we had before. We want to see that this way of calculating transmission from our simple conceptual model gives us the same answer as the other way. I'll mention, and I don't know if it's useful or not, these slides are already online, and there's also a set of handouts that's online. And some of you may want to check in the morning which lectures have handouts, because you can print out the handouts and scribble on them. You should not rely on the handouts. You definitely want to take notes, but it's very nice if you can just take notes on the parts that are going on in your brain, and you already have the handout as a, oh, there's a word I'm missing. Platform, no. Substrate. I don't know why that's the best word anyway. Since about last year, I often suddenly can't think of words, and it bugs me. Good. So now we've talked about the two key processes in our model and how we're going to estimate them for our ODE, and this is the ODE, and you are absolutely not allowed to be scared of it because it's absolutely dead simple. If I asked you to solve this ordinary differential equation, that's extremely hard. Like, I would not even want to solve this ODE, and you are allowed to be scared if somebody's trying to force you to solve an ODE. But if somebody's just showing you one as a way of explaining what they're doing, it's dead simple, and you have to not be scared of it. All this is saying is that I'm assuming each of these boxes are changing continuously and sort of adjusting their rate of change continuously, and this is the rate at which it's changing. So at any instant, the number of susceptibles is changing at this rate, representing the infections. At any instant, the number of infectious individuals is changing at this rate, which is representing the number of infections minus the number of recoveries. And that's all it means, and that's usually all you need to know about it. And I think that's one of the main themes of my lecture. And we're now going to construct a spreadsheet implementation. We're going to start as a discrete time model, and then we're going to talk about how it might link to an ODE, and we're just going to do it